Well, good afternoon, everyone. Today, I'd like to talk to you about some work that we've been doing the past several years to try to model the outer planet magnetospheres, and I'm going to concentrate in particular on Magnetosphere-Ionosphere coupling, and particularly at one of the planets. This is a slide I put together for my colleagues at NSF, trying to convince them that they should create a new program to fund comparative magnetospheric research, and telling them how important it is. And I'm going to use it as an introductory slide here. What I'm going to do today is I'm going to very briefly give you introductions, most of which have already been discussed this morning and in the first talk this afternoon, at the Earth and Jupiter. And then spend most of my time talking to you about Saturn, and in particular the Magnetosphere-Ionosphere coupling at Saturn. Starting out with the Earth, the things you know. It's a magnetized planet. For today's talk, it's a slow rotator. I'll talk briefly about the interaction to the bow shock. This plasma comes primarily from the solar wind and the ionosphere, as we've heard this week. And it's a reconnecting magnetosphere with southward IMF. This is just a cartoon, a slide I'm using as a cartoon. Thank you. Oh, that's better. It's the noon-midnight meridian for a simulation, and the velocity is the color coding, and I've drawn in some magnetic field lines. The point I want to make is typically it's a reconnecting magnetosphere, and in the simulations, it's completely dominated by reconnection as far as driving flows in the magnetosphere. There's typically 50 to 100 kilovolts across the magnetosphere. There also are viscous type interactions, and I'm going to talk about those for just a second, but they're smaller, about 20 kilovolts, and the simulations seem to be very consistent there. You can buffet the magnetosphere by changes in the solar wind dynamic pressure, but it's a fairly stiff obstacle compared to the outer planets to pressure changes. Finally, this is misleading, and really misleading in the sense that reconnection doesn't occur in a nice form like this might suggest. It's very episodic and very dynamic, creating dipolarization fronts, narrow channels of flow and of reconnection. But at Earth, we have both reconnection, dominant, and viscous type interactions, and here's an example of that. This is the same simulation. Here I've plotted the electric field now, and as the background colors, and then flow vectors on top of that. What I want to show you is this is the shape of the boundary. It has waves propagating on it. And I've drawn in BZ here as an equal to 0 as an indication of where the magnetopause is, and Vx equal to 0 to kind of delineate the boundary layer in the simulation. Very suggestive that the mechanism is Kelvin-Helmholtz waves. Well, we can actually check that. We can do the linear stability condition, and we can right around 9 o'clock local time here, where it seems to go unstable, and we find that indeed that's where this term becomes larger than these two terms, and that's consistent. We can also, because it's a simulation, we can calculate KD, where K is the wave number, and D is the thickness, and it comes out to be just what you'd expect from linear theory. And indeed, the formation in all the planets, you'll see, is pretty much consistent with what you saw from linear theory. Okay, now, Jupiter, again magnetized, as you've already heard several times. It's the most rapid of the rapid rotators. It's unfortunately complicated for simulators by having a 10-degree tilt, so that it goes up and down. Io is the main planet, as Fran pointed out this morning. We do have a bow shock. I'll talk just very briefly about that. But remember, for northward IMF now is the case for which reconnection occurs, and definitely has Aurora. And I will argue a very dynamic magnetosphere. This is just a couple of snapshots. Now, it takes 5 hours or so for the solar wind to convect over the dayside magnetosphere. It's very different than say, in the Earth, where it's 10 minutes or so. What I've plotted here is just the north-south component of the magnetic field. Over here, the velocity, both the speed and the vectors showing it. That the dominant flow, as we've heard several times already, is rotation here in the inner part of the magnetosphere. There is reconnection occurring. Jupiter has a very, very long tail, so we know reconnection is occurring. It's occurring back here at about 125 or so in the simulation. In this simulation, Jovian radii, and I'll come back to these structures on the next figure, which is a little bit clearer to see. Just pointed out the bow shock and the magnetosheath. It's a more pointed obstacle than the Earth. So compared to the Earth, Jupiter has a very small magnetosheath, proportionately. Okay, this is a little later in that same calculation. And what I want to do is make 2 points. First, look at, here's where we had these would turn out to be plasmoid-like structures in this one, and we had another one here. So obviously something is changing, and what's changing is we find that reconnection turns off and on, even for constant driving. It reconnects, we drive a plasmoid down the tail, flow comes up, the reconnected flux tubes convect around, they come back again, they reconnect again. And it takes, because the flow is now the velocity has fallen below co-rotation, it takes, about 30 hours or so to get all the way around to where they can reconnect again. I put this in, though, primarily to show you. We get waves on the boundary at Jupiter as well. And here's a couple of snapshots showing them propagating on the dusk side. I have never seen them on the dawn side in Jupiter, and you'll see that's different than we see at Saturn. Now, here's the electric field, again, being plotted. I have not done a detailed analysis like the one I'm going to show you for Saturn, for Jupiter. And there's a very good reason. First, Jupiter simulations are the stiffest problem I've ever seen for an MHD code to handle. It's really very difficult to get the solutions you believe. Now that we've done Saturn, I'm convinced we have to go back and redo our Jupiter simulations with a much, much higher resolution code because these waves are very, very sensitive to the resolution in the code. Okay. The one I want to talk in greatest detail about is Saturn. Magnetized, the other rapid rotator. As Margie told you this morning, it has this interesting property of having essentially zero tilt, but having the periodicity continue out into the magnetosphere, and she presented the simulations that Shinja and she have done in which they use the vorticity from the thermosphere to drive the flows. We have not done this in this. I'm looking at other parts of the problem in our set of simulations. Northward IMF again for reconnection, and we know about the Aurora. It's rather beautiful. I guess everybody has to show this figure or a version of it today when they're talking about Jupiter. This is the version that I have. It makes the same point that Tom made, the same point that Margie made. In fact, I stole it from her. And it shows basically that, again, it's J cross B force here. You can't see it down here, but there's another one in the ionosphere slowing it down and connected by field-aligned currents. So we really want to look at those field-aligned currents. Nobody has done this at this meeting, but I want to stop and just tell you how we run the simulation, because I want to make a very, very, what I think is a very important point, and why we're redoing a lot of the material that we've done. We solved the single fluid resistive MHD equations. I'm going to show you a case in which there's symmetry. We did not do, for the run I'm going to show you, we did not do the southern hemisphere, although we have done runs with that, and I'll explain why we didn't do the southern hemisphere. So we use mirror boundary conditions, and we use open free boundary conditions at all the other boundaries. We do a lot at the inner boundary, which is set at 5 Saturn radii, simply because the Alfvén velocity just gets too large as you get close to the planet. We have the ability to control an Enceladus source, and which is something we can use as a knob to turn. And this has happened to be the value we chose for this particular simulation. But the crux is this part. This is a huge, huge computational grid. And what we found in our calculations is to properly get, in particular, the waves to give us very, very good, believable solutions, we had to go to an extremely fine grid in the calculation. And now we're going to apply that back with a new version of the code to Jupiter. The ionosphere is a very simple one. We just use the current continuity equation. We set the conductance, since we don't have any better indication of it, to 1 Siemens for the Pedersen conductance, and turn off the Hall conductance in the calculation. It's calculated on a 200 by 200 point grid. Okay, this I hope you can see gives you the pattern in the just above the equatorial plane from the Saturn simulation, and I've shown you 6 hours in the life of Saturn. It takes about a bit over an hour for the flow to convect across the day-side magnetosphere. For this particular set of simulations, it was first no IMF, then southward IMF, then northward IMF. So we had a magnetosphere already formed when we did it. And if you can see, and I can see, you can't very well, there's basically rotation around, it's almost perfectly rotating around in this region here. There's actually vortices forming over on this part. Here on the dawn side, the flows here in the tail go around the obstacle. I'll talk more about that in a couple minutes. And we've got to see some little ripples on the boundary. The ripples on the boundary have become quite noticeable as vortices. Now, 8 hours after we turned after reconnection began here at the day side, we finally get one of these rotated type plasmoids and reconnection forming in the night side, sending flows around in these two directions. This happened probably about an hour before this, or maybe an hour and a half before this particular part of the calculation. And it's sending flows back around here on the dusk side. And that's going to be important for what I show next. Oops. Okay. Now this is a blow-up of the simulation results on in the morning sector. It's the velocity plotted here as color code, with the arrows being the velocity vectors. And what I wanted to simply show is here's those waves, those wiggles I showed you at 10 hours, just starting to form waves on the boundary. By 12 hours, 2 hours later, they're just beautifully formed vortices. And it was doing a series of simulations by changing the grid spacing, the minimum delta x in the calculation, that we finally found we've got Kelvin-Helmholtz wave, or waves on the boundary, which are very well resolved. And it turns out that for the Kelvin-Helmholtz instability in particular, that's a critical issue, that it's very, very grid sensitive. This is then on the afternoon, and boy, that's a clean, sharp magnetopause. The vortices form a couple hours later, and again, beautifully formed vortices. The shear is caused by this flow coming around here on the addition to the shear from the flow coming around, opposite to co-rotation. Okay, we can do the very same analysis I did at Earth with this one. Again, this is the electric field and flow vectors. We can take the linear stability condition and we can evaluate it in our simulation, and we find that it goes unstable at about 9 or 10 o'clock local time over here, where this term becomes larger. And actually, at 10 hours over at about 9 o'clock, it was 1.2. And again, we can calculate KD for the thickness of the boundary layer, and it comes out to be about 1.3 in this simulation. So we're pretty confident now that what these are simply is Kelvin-Helmholtz waves forming at the same time that in this reconnecting magnetosphere. Well, what about reconnection? How important then is reconnection? We know that Saturn has a tail, so we know that reconnection has to be going on. But it has another effect in the inner part of the magnetosphere as well, and that's what I want to talk about next. It doesn't like to reconnect at Saturn in our simulation. It really doesn't want to do it. In fact, at the Earth, if you turn the IMF southward, bring it up to the thing, right at the subsolar point, it's going to reconnect, and you're going to put flux back into the tail. And it does it at the equator preferentially. It doesn't want to reconnect at the equator. Instead, it wants to reconnect above and below the equator. You get little O regions forming along the boundary here due to reconnection. The amount of erosion is relatively small. But it still has a very important effect in our calculations. And that is the fact that it changes the electric field here, such that if I take the northward and subtract the southward to show you the change that occurs, the change that occurs is such as to give us an E cross B drift right along the boundary, which increases the shear, which is why in this particular simulation the boundary went unstable to Kelvin-Helmholtz waves. And I've done a time-dependent contours, flow streamlines here, and you can see how it takes the plasmas and in this region and brings them out into that region nearer the boundary, and then gives you the asymmetry as a background onto the dusk side. Okay. The next thing I'd like to talk about is I've written down the simple Deldot J equal to 0, and calculated here is just the divergence of J. This is the famous equation that shows that it's simply equal to an inertial term plus a grad P term times crossed into B. Well, you can take the limits just to show you the familiar equations that you've seen in the literature many times. For J parallel here, you get grad P cross grad of the flux tube volume. If you take the other limit, in which the pressure term is not an important contributor, you get that dJ parallel ds is proportional to the total derivative of the parallel vorticity. So we can evaluate these, but we have to do it now both in space and time. We can actually calculate the values in the simulation. And what we find is the following, that you see the pressure gradients are largest here in the vortices, along the boundary, along the edge here where the flows are being diverted. Similarly, in the tail, you see the inertial term, and you can see they're also very much larger in the region of the vortices. Wow. Okay, I'm going to move on. Notice the scale difference. These are 500. This scale is 500 times bigger than this scale. The reason is you wouldn't see these if we plotted them on the same scale as this. Okay, these are the parallel currents. Blue is away from the ionosphere, so it's electrons going into the ionosphere. The strongest currents are caused by in the region, the current densities are in the region here of the flow vortices, the Kelvin-Helmholtz vortices. There's also considerable currents generated here by the shear in the vorticity in the tail region here. Everywhere that we calculated them, the flow shear was the dominant contributor to the parallel currents, not the pressure gradients. The currents in the ionosphere are plotted here. This is a view now the other way around because we mostly have auroral images from the southern hemisphere. So this is now dawn and this is now dusk. Again, these are the upward currents. These are away from the ionosphere. These are the currents into them. We see layers of current structures here, which are from the region of vorticity in the tail. And right when we see the Kelvin-Helmholtz waves form, we see up and down currents in this region over here where they are forming. Similarly, later on, they continue, but we also see these ones on the dusk side form. Okay. Here, this is actually the vorticity plotted, but I mainly showed it to give you a concept of the feel for the overall regions of the magnetosphere. And then these are the same plots of the ionospheric currents in our simulation. And they come from the region of the vortices. These up and down currents in this region come from the regions of the vortices here in the tail. Similarly, on the dusk side, over here later on. And then in the region where we see vorticity in the tail, we also get parallel currents. Okay. What I've done is this. I did a simple model in which I assumed the night relationship and calculated the power to the ionosphere from in the currents in our simulation. And the number that I came up with is about 70 gigawatts. In the last couple of years, there have been papers, including a paper by Ray et al., that pointed out that this assumes that the night relationship assumes that you have minimum density near the equator, and we have a plasma sheet back there. I've actually gone through and done some calculations to see how big an error this made. So I'm now going to put this as a lower limit to the power from the parallel currents in the system. A smoking gun. I really was excited when I saw this particular paper come out. This is by Denny Grodent and shows the structure here on both sides on the in the magnetosphere. In the images of the aurora, he thought that they were Kelvin-Helmholtz waves, and they're certainly like the current patches that we see in the MHD simulation. Okay, I'm going to finish because I haven't shown you the convection pattern, and I did not make this plot. Low latitude convecting flows. This is a two-cell system, and boy, it did not reproduce well here. It goes in a very complicated two-cell pattern as well, with smaller vortices flow inside it. It's quite complicated, but it is basically a rotation plus a two-celled pattern. The final thing I want to mention today is calculate the thermal energy flux to the ionosphere. That's what this colored on top of the flow pattern is colored shading. And what I just want to show you is it maximizes in the cusp region, and there is very bright aurora seen in the cusp region, so there may be some relationship. There's about 2 gigawatts here. Okay, there's my summary. Reconnection for Kelvin-Helmholtz waves are found in all three, I believe, although we want to redo the Jupiter calculations. Reconnection is dominant at Earth for driving flows, less important at Jupiter and at Saturn. Vorticity is the dominant driver of all the currents that we see in our simulation at Saturn. The largest parallel currents, the current density at least, is from the Kelvin-Helmholtz waves. Greater than 60 gigawatts is our estimate of the aurora of the precipitation power, and we see thermal energy flux concentrated in the cusp region, and I made it. And thank you.
The paper's open for discussion. How about Dan Baker?
So from the Earth point of view, I think one of the major accomplishments that we explored some on Tuesday was a form of cross-scale coupling. How does one go from driving a system by its energy source through intermediate steps to ultimately producing very energetic electrons that in strong magnetic fields radiate. So from an astrophysical standpoint, this is what the systems are about. This is what we can see remotely. Not to pick on you particularly, but I haven't seen a lot of that exploration here for the other planets of really how are we doing on understanding how those systems work, going from the driver all the way to things you could remotely sense when there is no spacecraft there.
I think there's been less done. That would be my general conclusion. There's been less done in the outer planets. But I've got to give an editorial comment. Since you gave your introduction about the Earth, I didn't have time, but I begged Rick to give here that I could give a second part of the talk, which is to show some of the new results in which we've taken PIC codes, combined them with the MHD codes to do some of this cross-coupling. And all I can tell you is come see me. It's really exciting stuff.
Alex, wait till you get us a microphone.
Well, thank you. I thought that was very nice. I was curious, though. One issue, especially if reconnection is very important to the formation of the KH. It should be very sensitive, not just to the grid resolution, but also to how you choose your resistivity. And I'm curious how you adapt the resistivity model you use for Earth to one of these larger outer planet.
For all of these, I used a uniform resistivity.
Oh.
So it's just A to J, and the only thing that gives it a dependence then is the J.
Okay.
Because I don't know how to do it.
Sure.
Well, I'm going to ask a question. Kelvin Helmholtz is most easily destabilized for either parallel or anti-parallel fields on the two sides. And I gather you had anti-parallel fields.
That's right.
Have you done any runs where you put a tilt in the field?
The answer is yes. They're so much more complicated, Margie. I'm
it's
working
so much
on them.
closer to
But they're more
the-
close. I mean, at Saturn, the field is, it's laying over on its side. So it's a very interesting question. The answer is in the lower resolution runs that you still do see them, but I want to redo them with it on its side and with a large BY and with the high resolution calculation, because it's so important, because they can disappear if you don't get it right. That's one of the real big lessons of this particular set of numerical experiments. But I got a very nice abstract, AOGS, on Monday, in which my name is on a paper saying we've got a new way of getting very high resolution in the codes, and I've written back to the person who put my name on the abstract saying, oh, what did I do?
Time for one more question? I don't see anybody, so thank you.